So, hello everyone, we are back to our plasma class. So, what we will be studying in this class ECR plasma sources and formation of plasma seed. We already started introduction to our ECR plasma devices in the previous class, and here it is actually how uh, a a typical RF plasma ECR plasma device looks. The essential components are shown on the right side diagram. These CCR sources are devices that are usually used to produce highly charged ions, means multiply charged. So, it is not say argon, it may be argon plus plus, argon double plus kind of thing, and the sources are extremely useful in ion beam production, for accelerators, then surface processing in semiconductor technology and in medical areas. So, we discussed about that, and let us now see what are the major components in this ECR plasma devices. So, you can see on the right hand side it is having a magnetron device which produces 2.45 gigahertz microwave. So, this is a microwave generator. Then it is having a guide to couple it with the plasma chamber. So, this is the chamber, and there are two magnets. What you are seeing, they are usually electromagnets, and they produce an axial magnetic field over here in this zone. Okay. So, that is a magnetic field which you require to make the particles gyrate along the periphery, in a circular path. So, whenever there is a magnetic field and charged particles are there, they start orbiting around the magnetic field, you already know. What will be the this radius of gyration? You know, R is equal to mv by bq. M is the mass of the particle, b is the velocity, b is the magnetic field, and q is the charge. So, depending on your magnetic field and the charged particle, you will be having some orbit, and v is basically determined by the kind of temperature that you are able to create over there. So, radius, they will be orbiting in some radius. Now, what happens, this magnetron provides some microwave. Essentially, you are applying an electric field that may be a linearly polarized or it may be circularly polarized. So, depending on the case, I will be explaining that with one say numerical example. What should be the magnetic field if you want to energize the plasma in a cyclotron way. So, this is having this chamber, and then when this plasma comes out, then there is a, you see here, there is a gas inlet where the gas of your interest you can insert here. For example, here some CH4 is inserted, and these are the ports through which the CH4 comes out. They get ionized, and they form different types of combinations like CXHY or CC or H plus kind of thing, and they start depositing on the surface. So, various kind of applications where you can use this kind of devices. Now, an ECR ion source operates by injecting the microwaves into the plasma chamber containing a low pressure gas. So, this is the chamber where you inject the microwave using this magnetor device and the guides. So, it is having standard configuration like sliding sort, mode converter, stub tuner, coupler. So these are all there as a part of the standard configuration of microwave coupling. When you are injecting the microwave in this, so as I told you that you can introduce it in different modes, uh, which is suitable for the kind of application that you are going to use. Then the magnetic field is produced by this magnetic coil and applied to the chamber when the frequency of the microwave matches with the natural cyclotron frequency of the electrons in the magnetic field that we have applied, then resonance occurs. The resonance, what it does, efficiently imparts the energy to the electrons, heating them to very, very high energies. These energetic electrons then collide with the gas atoms or molecules which are there and then ionize them. So the process, because of resonant kind of behavior, it is very efficient and produces multiply ionized atoms, multiply charged ions, depending on the electrons it is able to remove. The ions are confined within the magnetic field and can be extracted to an electrode system for use in various purposes. As I told you that it can be used for this ECR ion source in accelerators. So what are the basic components that it is having? It is having a microwave generator. Typically it operates at 2.45 gigahertz and provides the energy that is required for electron heating. Then we are applying a magnetic field, what is that? Then we are using a coil and producing an axial magnetic field which is confining the plasma and facilitating the resonance by gyration. So this will be more clear when I go for that exact example. Then there is a plasma chamber. So you do have a vacuum system and a chamber so that you can create a low pressure zone where this ECR mechanism can take place. Then of course there is a gas injection system which injects the desired gas into the plasma chamber in a controlled manner. So this not only uses the this thing plasma gas. So one gas is over here which you are using to produce the plasma, and there are other process gases which you are injecting through this distribution ring. There are equispaced some holes in this, evenly placed. So through these holes the gas comes in and they get ionized by the plasma and forms the desired does the desired effect that you are looking for. So this gas injection system is absolutely necessary for the kind of plasma you want to generate. Then ion extraction system is required for drawing the ions out for acceleration or some other purpose, other application purpose. Then sometimes you require a substrate heating system for the CVD kind of job. So this is your substrate, and at the bottom what you are seeing, so this is the heating arrangement. So you can put heating coils over here, and through a feed through you can heat the substrate to the desired temperature, so the desired deposition CVD can take place, plasma CVD basically, so that can occur on the surface of the substrate that you have inserted. So and this is the vacuum system which is maintaining the desired vacuum in the system in a time continuous manner. You remember that some gas you are injecting through here, some gas you are injecting through here, and the pumping system should be such that it can maintain the pressure inside the chamber in a very stable manner. So you have to control the sucking system in a way that the pressure that you have created inside the chamber is maintained without time variation. Now, I was telling you for this example where I just want to tell you how the ECR plasma is generated. So, this is very important actually, because to understand the physics behind, the mechanism behind the formation of the electron cyclotron resonance phenomena. So, the name itself suggests that there are some electrons, there is some cyclotron motion, and there is some resonance. So, each of these E, C and R we will be explaining in this example. Now, what we are seeing in the first block, we have written Q V cross B, that is definitely this is a vector equation. So, Q V is B sin theta, and the magnetic field, as I have shown in this diagram, it is pointing inward, so pointing to the board. So, you know that these are electrons. So, if you see that V cross B and take the sign, you will see that Q V cross B is pointing inward. So, that is what is required. So, the direction what we have applied, you see these red arrows, they are basically showing the gyration direction. Okay. Now, you know that if there was nothing else, you had only magnetic field and some charged particle, then as I told you earlier, the radius of gyration will be equal to mv by bq. We are starting this in since our school days, so there is no question of forgetting this thing. So, R is mv by bq, mass, and then this is velocity, this is magnetic field, and this is the charge. So, if no other effect was there, then the charge would like to orbit with this radius for ever and ever. Now, when we are now applying external electric field, the electric field, the moment we apply, the charge will interact with that and it will get accelerated, and the force will be Q into E and acceleration will be QE by M. Very simple. Now, when the charge is originated here and it is want to gyrate like this, and what you have done, you have applied one electric field over here. So, what is there? Its energy is increased, velocity is increased. So, now you see that R is mv by bq. Now, V is increased, so R is increasing. Okay. And the magnetic field that you have kept is constant. This Q is constant, M is constant. So, what you are increasing? You are increasing the V by how? You are, when the particle is over here, then you are applying an electric field. Okay. What is the direction? That matters. The direction is in this way. Okay. The direction is in this way. The red big arrow is the direction of the electric field over here. Now, when the particle is rotating, got the energy and it has increased its radius of gyration, because R is mv by q, V is increased because of the electric field acted upon that. So, velocity increased, R has increased. Now, R is here. When it has reached here, we are using a linearly polarized electric field. That is, the electric field is oscillating only in the x direction. Suppose this horizontal direction is x. So, once it is positive x, next time it is negative x. And from this orbit, you know that if that is the case, then if I want to energize that electron using external electric field, then at this point I need to apply the electric field in this way. When I have done that, the radius of that gyration has increased, and when it has reached here, I need to apply an electric field if we want to accelerate, of course, exactly in the same direction. So, now I need to put it over here in this direction. Then I have applied the energy again. So, velocity is increased further, radius also increased further. So, it is now here with the increased radius. So it is gradually moving outward from the center. Now at this point, if I want to accelerate the particle, I need to apply another electric field at this point, so that the direction of the electric field and the direction of velocity, they are matching together. So again the velocity is increasing. So velocity increasing means the radius is increasing. Now the particle is over here. So now it is the right time to apply another electric field. So if you move from center to the outer, so this is this direction, okay. So next time you are putting in this direction, opposite, then you are coming in the opposite direction, then again opposite direction. So you are moving the direction of the field this way, then that way. So you are synchronizing the rotation frequency with the frequency of the applied electric field. Now you know that when a particle operates in a this magnetic field, then the frequency of gyration, omega is Eb by m. Omega is the angular frequency, omega is 2 pi f. So linear frequency, if you want to know, then Eb by 2 pi m. Now this is the frequency of gyration. Now if we want to match this frequency with the frequency of the applied electric field, so which is here 2.45 gigahertz standard commercial microwave frequency. So this frequency, if you want to match with, then this is telling us that your B is equal to, this B is somehow dropped here, you don't mistake it by saying that it is subscript of B, it is actually B, this has no relation with this F in this configuration only. So B is equal to, I take this one 2 pi F divided by E, that is what is coming, isn't that? So B is equal to, if you take it from here, B is equal to this 2.45 into 10 to the power 9, which is the applied microwave frequency, into this 2, this 2 is there, then pi 3.142, then m 9.1 into 10 to the power minus 31, divided by this charge, that is charge of the electrons is 1.6 into 10 to the power minus 19. So what you are getting here now? You are getting, if you do the calculation properly, and you will be able to see 19 into 9, 19 plus 9, 28. So 10 to the minus 3 is coming over here, and then you multiply them and divide by 1.6, and you are getting 87.56 millitesla. So that is giving 875.6 Gauss. So the magnetic field that you need to apply for the resonance to take place, that is it will match with the microwave frequency, electric field frequency of variation with the same, will be the same as the gyration frequency. So then the resonance will take place, and for resonance with your this microwave frequency, standard commercial microwave frequency 2.45 gigahertz, we see that the required magnetic field will be 875.6 Gauss. So now you are very much clear that how you are able to impart the energy in an ECR planar source in a resonance manner using a linearly polarized electric field in this case. Now suppose the velocity vector, as it is moving, the particle is moving, it is continuously changing its direction. So now in this direction it is changing, now it is in the opposite direction, then changing, now again in the previous direction, then changing, now in opposite direction. So the velocity vector is continuously changing. Now what if you are able to polarize the electric field in such a way that it is always in the direction of the velocity vector? So that will be a circularly polarized light. So it is now the particle is rotating and its velocity is changing, and the field is also in the same direction. So that will be a very efficient way of imparting energy in this kind of plasma. So you can do that using a circularly polarized electric field. So they are also possible. So now you understand the how one generates the resonance in the cyclotron motion of electrons. So this E, C and R, electron cyclotron resonance, you are now able to understand how the cyclotron motion occurs due to the existence of the axial magnetic field. The cyclotron motion happens and the resonance occurs because you have chosen the magnetic field in such a way that it matches with the microwave frequency 2.45 gigahertz, and that's how the energy is getting coupled into the system in a resonant manner. So this is how the ECR plasma source works. Now I will introduce you to the area of plasma sheath. I will just do the introduction in this class, and in the next class I will be going into the details. So what is plasma sheath and how it works? What is the nature of that? Whether it is electrically neutral or it is non-neutral. We know that plasma is neutral, but you will be surprised to know that this plasma sheath region is absolutely not neutral. It is highly charged region. It is not neutral at all actually. So the problem of sheath formation at the plasma boundary occurs. This is of importance nearly all applications, and it occurs in such a small region, such a tiny region, that it is very difficult to explore experimentally, because it is say some millimeter or less than a millimeter. How will you put your probe to explore that region where all these phenomena are happening? All these phenomena are happening. So multiple phenomena, they are happening over there, as we come to know as we progress in this class. So this problem is one of the oldest problem, and yet not fully understood. As I told you, it is due to the fact that it is so thin layer where all these phenomena are happening, but they are very important as far as the application is concerned. So we come to how the plasma sheath forms. So in a plasma, the number of positive and negative charges are nearly equal. As you know that overall charge neutrality is maintained, macroscopic charge neutrality is maintained, and within the device sphere this is not, but beyond the length scale of device sphere, this charge neutrality is maintained. However, when the plasma comes in contact with material surface, the electrons being much lighter and faster than ions, they reach the surface first, and this causes the surface to gain some negative charge, because the ions are also moving, but they are not that fast. So electrons are bombarding the wall at a much faster rate because of their lower mass and higher mobility. So this surface is getting charged so negatively. Then they start repelling further electrons to reach the surface, and the negative polarity that is developing on the surface, what they are doing, they are attracting the positive ions towards that. So this imbalance actually forms a thin layer called the plasma sheath near the surface. So what is there? What are the very special feature of this layer? The electrons are depleted. Why? Because of the negative charge on the surface, they are repelling the electrons, they are not allowing them to reach that region. But that is very favorable for the ions, positively charged ions. So in this region, positive ions dominate, and as the charges of one polarity is populated more in that region, so that is definitely generating an electric field in that region. Now what is the dimension of this seed region. So this is of the order of say few dBi length only. Okay, the thickness is of the order of few dBi lengths. The electric field directs the ions towards the surface, influencing the etching deposition via plasma process. You know, one of the important application of this plasma is in the semiconductor industry. How do they work? They do etching by this ion bombardment. Okay, so if the sheath affects the motion of the charged particles, so that can influence the process that you are looking for. So unlike the bulk plasma, which is macroscopically neutral, as I already told, that the sheath is non-neutral. A net charge exists in that region. So this is what is plasma sheath, how the plasma sheath forms, and what are the very special features of this plasma sheath. So this sheath zone is electron depleted. There are positive ions which dominate over there. There is an electric field which is developed because of the charge imbalance. The thickness is very thin, only few dBi lengths, and the field directs the ions toward the surface, influencing the plasma etching or deposition process. So unlike bulk plasma, the sheath is non-neutral and a net charge exists in the region. So these are the features of the plasma sheath region. Now here I will just explain you how the plasma sheath is being formed. What we have taken here, just for explanation purpose, that the bulk plasma potential is 0 here. Not necessarily it can have some value, but here we have taken it like this for relative comparison. And you see here that the net potential between the cathode and the anode it consisting of two regions. One is this region where the cathode potential is increasing, then it is reaching the bulk plasma where potential is near 0, and then it is dropping. So the net voltage drop in the plasma, whatever you are applying, it is basically getting affected in the region very close to the electrodes. So this is the this is called anode drop and this is called cathode drop. So these two regions are the locations where the major potential drop is occurring, keeping the bulk plasma at certain almost constant potential. There is a drop, but that drop is only this much. This is the plasma drop. And the major drops, whatever you are applying between the electrodes, that is occurring, one in the cathode drop region and another in the anode drop region. So with this introduction, we will start more elaborate exploration of this plasma sheath. We will go through some mathematical derivations, so either as a part of the tutorial or in this itself. So we will try to understand the physics inside the plasma sheath in a more elaborate manner in the coming classes. So I stop here and meet you in the next class. Thank you.